This video is about how to construct summaries called the data reduction, commonly known as the descriptive statistics. The measures of central tendency, also known as the averages, are the mean, median, and mode. In which when we speak of the mean, the most common average, we refer to it as the arithmetic mean, which is the sum of the observations divided by the number of observations. It is also referred as the balance point of the data set. In symbols, some use the capital M, but to differentiate the population and the sample mean, we use the Greek letter M, which is mu for the population mean, and X bar for the sample mean. Consider here that capital N is the population size and small n for the sample size. Let's have the first example wherein a marketing specialist gathered 5 randomly selected customers and their age are 19, 25, 32, 27, and 41. And we are asked to find the mean age of these customers. And since it was stated that these are randomly selected customers, then we are sure that these are from samples. And given these 5 observations, then the value of our small n is 5. And since we are asked to find the mean age, then this refers to the sample mean, which is X bar, which is the sum of the observations over the number of observations, which is equal to 5. And getting the sum of 19, 25, 32, 27, and 41 divided by 5, that gives us 28.8. Thus, we can say that the mean age of these customers is 28.8 years. On the next example, a researcher wants to determine the cholesterol level of all the 6 residents of Guyan Island. Observations are as follows: 120, 120, 140, 150, 160, and 190. And we are asked to compute for its mean. And since it is stated that these are all the 6 residents, then these are the population. And since we have 6 observations here, then the value of capital N is 6. And since we're asked to compute for its mean, and this is about the population, then we're going to make use of mu, which is similarly the sum of the observations divided by capital N, in which again this is 6. And getting the sum of the observations divided by the number of observations, we're going to have 146.67. Thus, we can see that the mean cholesterol level of the residents is 146.67 milligrams per deciliter. Continuing with the next example, wherein the same researcher suppose wants to determine the cholesterol level of all the 6 residents of Guyan Island. But due to some constraints, he can only get 3 of the population, wherein the researcher observed the following cholesterol: 120, 140, and 160. And we are asked to compute for its mean. Now, since these are 3 of the population, then these values are coming from samples. And since there are 3 observations, then our small n is 3. And this mean refers to the sample mean, which is X bar. And similarly, we're going to compute it as the sum of the observations divided by the small n, which is 3. And computing for its mean, we're going to have 140. Thus, we can say that the mean cholesterol level of the residents is 140 milligrams per deciliter. In which this shows that this sample mean is an estimate of the population mean. Remember that statistics is an estimate of the parameter. So this value of X bar is an estimate of this value of mu. By theory, if X sub 1, X sub 2 up to X sub n are random samples from a population with mean mu, then the sample mean computed as the sum of the observations over the sample size is an unbiased estimate of the population mean mu. In simple terms, as long as the samples are selected at random, then its sample mean is neither bigger or smaller than its population mean. Another example is using this frequency distribution table where asked to find the mean, wherein the observed values are 20, 29, 30, 39, and 44. But this frequency tells us that 20 occurred twice, 29 occurred 4 times, 30 occurred 4 times, and 39 occurred 3 times, and 44 occurred 2 times. So if we're going to compute for the mean, suppose this is from sample, we're going to have 20 plus 20 since there are two 20s as stated here, plus 29 plus 29 plus 29 plus another 29, and 30 which occurred 4 times, so we have 30 plus 30 plus 30 plus 30. And 39 occurred 3 times, so we're going to have 39 plus 39 plus 39. And lastly, we're going to have 44 which occurred 2 times, so that's 44 plus 44. And then divided by the number of observations in which that is 15. In which this may be simplified by 2 times 20 plus 4 times 29 plus 30 times 4, 3 times 39, and twice of 44. In other words, we may just multiply 2 and 20, which is this one, 4 and 29, which is this one, 4 and 30, which is this one, 3 and 39, and 2 and 44. In other words, x bar here is simply the sum of f and x. So we have 2 and 20, 4 and 29, and so on. So that's the sum of product of f and x all over the total observations, in which in this case is 15. In which we're going to have 481 over 15, which is 32.07. Although in this video, I only presented how to compute for the arithmetic mean, there are other means which completes the Pythagorean means. The harmonic mean, which is the reciprocal of the arithmetic mean of the reciprocals. These are commonly used in rates. The geometric mean, which is the nth root of the product of the n observations. Next, we have the median, which is the middle value of the data set. Thus, it separates the data into lower half and the upper half. In symbols, while some use MD or MDN, in this video, we're going to make use of X curl, which is an X with a tilde above. Using the same example, wherein a marketing specialist gathered 5 randomly selected customers wherein their age are 19, 25, 32, 27, and 41, this time we're asked to find the median age of these customers. So the first thing that we have to do is to arrange the observations in ascending order. So starting with the lowest, which is 19, followed by 25, 27, 32, and the highest, which is 41. Then the next thing we have to do is to find the value of the middle observation, in which in this case is 27. Thus, we can see that the median age of customers is 27 years, which tells us that below 27 years is on the lower half and above 27 is on the upper half. And using the previous example, wherein the researcher who wants to determine the cholesterol level of all the 6 residents of Guyan Island, wherein the observations were 120, 120, 140, 150, 160, and 190. And to find the median, we have to arrange first the observations from lowest to highest. Now, since we have 6 observations here, it is clear that the middle observations are the values 140 and 150. So, to find its median, all we have to do is to get the middle value of these 2 middle values. And obviously, that is 145. Thus, we can say that its median is 145. So, we can say that the median cholesterol level of the residents is 145 milligrams per deciliter, which tells us that below 145 is on the lower half, while above 145 is on the upper half. As we can see using the previous examples, wherein in example number 1, we have 5 observations, and if we're going to assign x sub 1 as the lowest observation, x sub 2 as the next one, and so on, until we have x sub 5 as the highest observation, we have its median, which is the third observation, or x sub 3. On the next example, wherein we had 6 observations, and similarly, if we're going to assign x sub 1 as the lowest observation, up to x sub 6 as the highest observation, in which our median is the middle value of 140 and 150, which happens to be x sub 3 and x sub 4, then if we have 6 observations, the median is the middle value of x sub 3 and x sub 4, which is denoted by x sub 3.5. Thus, we can say that if we have 5 observations which are arranged from lowest to highest, then its median is the third observation. Similarly, if we have 6 observations arranged from lowest to highest, then its median is the middle value of the third and the fourth observation, which is denoted by x sub 3.5. If we have 7 observations arranged from lowest to highest, then it's clear that the fourth observation denoted by x sub 4 is the median. Similarly, if we have 8 observations arranged from lowest to highest, the median is the middle value of x sub 4 and x sub 5, which is denoted by x sub 4.5. And if we have 11 observations arranged from lowest to highest, then its median is the 6th observation. So when we had 5 observations, the third observation is the median. When we had 6 observations, the middle value of the third and the fourth is the median. When we had 7 observations, the middle value is the fourth. When we had 8 observations, the median is the middle value of the fourth and the fifth observations. And if we have 11 observations, the median is the 6th observation. So if we have x sub 1, x sub 2, x sub 3, up to x sub n, how are we going to find the median? As we can see here, when we add 1 with the number of observations and get its half, we can get the position of the middle value. Add 1 from 6 divided by 2, we're going to have 3.5. Add 1 with 7 divided by 2, we're going to have 4. Add 1 with 8 divided by 2, we're going to have 4.5. Add 1 with 11 divided by 2, we're going to have 6. So if we have 21 observations, it is clear that to find the median, all we have to do is to add 1 with the number of observations, then divided by 2. So 21 plus 1 divided by 2 gives us 11. So we can see that the 11th observation among the 21 observations arranged from lowest to highest is the median. Similarly, if we have 50 observations, then its median will just be add 1 then divided by 2, so that's 50 plus 1 divided by 2, that is 25.5, which tells us that the median is the middle value of the 25th and the 26th observation if the 50 observations are arranged from lowest to highest. Thus, we can see that if we have n observations, the median is simply the value of the n plus 1 over 2th observation. Or in other words, that is x sub 1/2 of n plus 1. Although in this video, I am using less than to denote observations arranged ascendingly, strictly less than or equal should be used when there are tied observations. So to find the median of the data presented in this frequency distribution table, wherein this shows that we have 2 20s, 4 29, 4 30s, and so on. And since there are 15 total observations, so this is like your x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, and so on. If we have 15 observations, then the median is just x of 15 plus 1 divided by 2, which happens to be 16 over 2, which is 8, and that is 30. So we can say that the median here is 30. Although in most cases, the mean and the median are close to one another, in some situations, the mean and the median are far from one another. Remember that the mean is the balance point, while median is the middle value of the data set. To illustrate, let us have these observations, wherein the computed mean and median are both 30. And if we're going to illustrate these values to a lever, in which each value is represented by a ball, 2 values of 10 will give us 2 balls at position 10. 3 observed values of 20 will give us 3 balls at the position of 20. 5 values of 30 will give us 5 balls at the position of 30. And likewise, we have 3 observed values of 40, so that gives us 3 balls at the position of 40. And 2 observed values of 50 gives us 2 balls at the position of 50. And suppose this is a seesaw, wherein we're going to put a support to this level for this to be balanced. We're going to put the support at 30. since that is the balance point. And at the same time, it is the center of the distribution. Now suppose let's add another observation, which is 222. And using the same figure, we're just going to add another ball at the position of 222. Now for this to be balanced, we're not going to put the support at 30 because putting the support at 30 will surely not make this seesaw balanced. So we have to move the support a little bit on the right for it to be balanced. And computing for the mean, when 222 is included in these observations, we're going to have a mean of 42, which tells us that if we're going to put the support at the position of 42, it will be balanced. So 42 here is the balance point and not the center of the distribution. What I have illustrated shows that the mean can easily be affected by an outlier while the median is not. Similarly, if we're going to have these observations in which the median is 30, and we're going to illustrate it using the same procedure a while ago, putting the support at the position of 30 will surely not balance this seesaw. So to find the position, all we have to do is to get the mean, in which the mean of this distribution happens to be 38.1. Which tells us that if we're going to put the support at the position of 38.1, it will make this seesaw balanced. Thus, we can see that the median is a better measure of central tendency as compared to the mean, as it remains to be the center or the middle of the observations when there is an outlier or when the data is skewed, or in other words, when it is not symmetric with respect to its center. Moving on, let's have mode, which is the most simple measure of central tendency, as it is the observation or observations that appeared most frequently. In symbols, while some use MO for mode, in this video we're going to make use of X hat or an X with a caret above. Using the same example wherein a researcher gathered the cholesterol level of all the 6 residents of Guyan Island, and if we're asked to find the mode of these values, clearly, the value of the mode is 120. So we can say that the most frequent cholesterol level of Guyan Island is 120 milligrams per deciliter. And similarly, suppose we're asked to find the mode of the age of these customers, in which 5 randomly selected customers were gathered. Since there is no most frequent value here, then the mode does not exist. So we can say that there is no age which occurred most frequently. Another example is that a social media specialist wanted to determine the daily number of tweets of first-year college students. Result of 7 randomly selected students are these values. And since 12 occurred twice, 40 occurred twice, and the others occurred once, then the value of mode here is 12 and 40. So if we have 5, 5, 5, 6, and 7, the value of mode is 5. Since 5 occurred thrice, while 6 and 7 occurred just once. And if we add 6, still the value of mode is 5. And if we're going to add another 6, 5 occurred thrice, likewise 6 occurred thrice and 7 once, so the value of modes here are 5 and 6. If we add another 7, the value of modes would still be 5 and 6. And if we add another 7, the value of mode does not exist. Since 5 occurred thrice, 6 also occurred thrice, and likewise 7 occurred thrice, there is no value that appeared most frequently. Note that a set of observations with a single value of mode is called unimodal. When there are 2 values of mode, we call it bimodal. When there are 3, we call it trimodal. And if there are more than 3, we call it multimodal. Now, given the data presented in this frequency distribution table, since 29 and 30 occurred 4 times, while the others occurred less than 4 times, then it's clear that the value of modes here are 29 and 30. Now, the use of mean, median, and mode depends on the level of measurement of the data. For interval or ratio, we may use any of the 3. But the mean is said to be the best when the data is not skewed or when there is no outlier. For ordinal data, we should not use the mean, but rather we should use the median or mode. But since median is a unique value, others claim that it is better as compared to using mode in ordinal data. For nominal data, we should not use the mean nor the median, but we can only use mode. Now let's proceed to the measures of other position, collectively known as quantiles, which are the quartiles, deciles, and percentiles. While median, as we learned, divides the data into two, the lower half and the upper half, quartile divides the data into four. So we have quartile 1, quartile 2, which is exactly the same as the median, and quartile 3. Deciles, on the other hand, divide the data into 10 parts. Decile 5, which is exactly the same as the median, is on the middle, while we also have decile 1, decile 2, decile 3, decile 4, decile 6, decile 7, decile 8, and decile 9. Note that these 9 deciles divide the data into 10 equal parts. Meanwhile, percentiles divide the data into 100 parts. Percentile 50 is exactly the same as the median, quartile 2, and decile 5. Percentile 10 is the same as decile 1. Percentile 20 is the same as decile 2. Percentile 30 is the same as decile 3, and so on. Meanwhile, quartile 1 is the same as percentile 25, and quartile 3 is the same as percentile 75. And of course, there are other percentiles like percentile 46, percentile 63, percentile 97, and other percentiles from percentile 1 to percentile 99. So given the arranged observations from x sub 1, x sub 2 up to x sub n, recall that the median is computed as x sub 1 half of n plus 1. It's because the median divides the data into two equal parts. To compute for the second quartile, all we have to do is to replace the 2 in the denominator of median as 4, since quartile divides the data into 4. And since we're looking for quartile 2, then the numerator is 2 and still of n plus 1. It follows that in getting quartile 1, still the denominator of the subscript is 4 of n plus 1 and the numerator will be 1. And similarly for quartile 3, it divides the data into 4 equal parts, so the denominator is 4. And since we're looking for the third quartile, then the numerator here is 3 of n plus 1. Thus, we can say that in getting the quartile k as k from 1 to 3, then that is x sub k over 4 of n plus 1. Similarly, in getting, let's say, the fifth decile, since this is decile, then the denominator of x is to 10 since it divides the data into 10 parts. And since we're looking for the fifth decile, then the numerator here is 5 of n plus 1. It follows that the first decile is x sub 1 over 10 of n plus 1. Decile 2 is x sub 2 over 10 of n plus 1. And suppose we're asked to get the decile 7, so that is x sub 7 over 10 of n plus 1. Then we can say that the decile sub k, k from 1 to 9, is just x sub k over 10 of n plus 1. And thus, it follows that for percentile 50, that will be x, in which the denominator of the subscript is 100 since this is percentile, the numerator is 50 of n plus 1. In getting percentile 30, that is x sub 30 over 100 of n plus 1. In getting the percentile, let's say, of 67, that is x sub 67 over 100 of n plus 1. Thus, we can say that the percentile sub k, k from 1 to 99, is x sub k over 100 of n plus 1, which is shown in this slide. So if we're looking for the third quartile of this data, then after arranging the observations from lowest to highest, quartile 3 is computed as x sub 3/4 of n plus 1. And since we have 5 observations here, then n is equal to 5. So n here will be 5. So that will be x sub 3 over 4 of 5 plus 1, in which that is x sub 4.5, or simply the middle value of x sub 4 and x sub 5. And the middle value of 32 and 41 is 36.5. In which alternatively we may get this value, since x sub 4.5 means that that is between x sub 4 and x sub 5. So if we have 32 and 41, which are x sub 4 and x sub 5, to get x sub 4.5, all we have to do is to get the difference of 41 and 32, which is 9, take its half, so meaning this is 4.5, and another 4.5. So x sub 4.5 is 32 plus another 4.5. So meaning x sub 4.5 will be computed as 32, which is x sub 4, plus the half of 9, which is taken from 41 minus 32. Or in other words, x sub 5 minus x sub 4, which still gives us 36.5. In other words, suppose we're getting the value of x sub 3.2, that indicates that x sub 3.2 is somewhere nearer to x sub 3 as compared to x sub 4. So whatever is the difference between x sub 3 and x sub 4, all we have to do is to get the 0.2 of that difference and add it with x sub 3 to get this value. In other words, x sub 3.2 is x sub 3 plus this value, which is 0.2 of the difference between x sub 4 and x sub 3. Similarly, if you have x sub 11.7, for example, that may be computed as x sub 11 plus 0.7 of the difference between x sub 11 and its next value, which is x sub 12. If we're trying to get x sub 8.3, then that is x sub 8 plus 0.3 of the difference between x sub 8 and the next value, which is x sub 9. And if we're going to get, let's say, x sub 12.1, that is x sub 12 plus 0.1 of the difference between the next value from x sub 12, which is x sub 13, minus x sub 12. So if we're asked to find the first quartile of these values, after arranging them from lowest to highest, quartile 1 again, which is x sub 1/4 of n plus 1, in which the value of n here is 5. So that will be x sub 1/4 of 5 plus 1, which is x sub 1.5, which may be computed as x sub 1 plus 0.5 of x sub 2 minus x sub 1. And x sub 1 is 19, and x sub 2 is 25. So we're going to get 22. And since quartile 1 is 22, then a value lower than 22 is the lower 25%, and a value higher than 22 is the upper 75%. Another example, suppose we're asked to find the percentile 70 of these values. So that will be x sub 70 over 100 of n plus 1. And since we have 5 as the value of n, percentile 70 is just x sub 4.2, which is somewhere between x sub 4 and x sub 5, which are 32 and 41. And since this is x sub 4.2, this indicates that this value is closer to 32 as compared to 41. And computing for this, we have x sub 4 plus 0.2 of x sub 5 minus x sub 4, which is 32 plus 0.2 of 41 minus 32. And that gives us 33.8. And to get the 73rd percentile of these values, percentile 73 will just be x sub 73 over 100 of n plus 1. And since we have 6 values here, the value of n will be 6. So substituting n as 6, we're going to have x sub 5.11, which will be computed as x sub 5 plus 0.11 of x sub 6 minus x sub 5. So that will be x sub 5, which is 160, plus 0.11 of x sub 6, which is 190 minus 160. And that gives us 163.3. Which tells us that if this is the lowest and the highest value, and this is 163.3, then lower than 163.3 is the lower 73%, and higher than 163.3 is the upper 27%. For your exercise, find the quartile 1, decile 6, and percentile 91 of these values. All you have to do first is to arrange it in ascending order and assign the lowest value as x sub 1, followed by x sub 2, up to the highest value, which is x sub 11. And you will get these values for quartile 1, decile 6, and percentile 91. As for the measures of variability, also known as the measures of dispersion or measures of variation, we have range, interquartile range, the mean absolute deviation, variance, standard deviation, and the coefficient of variation. Let's start with the range, which is simply the difference between the lowest and the highest observation. So if we have ordered observations from x sub 1 to x sub n, range is simply x sub n minus x sub 1. So if we were asked to find the range of these values, all we have to do is to get the highest value, which is 41, and the lowest value, which is 19, and get its difference, and that is 22. So we can say that the range of the age of the customers is 22 years. Although in statistics we use the difference of the lowest and the highest observations to express range, consider that in most researches, range is presented by reporting the lowest and the highest observation.
Wow!
Note that range is used only in data in interval and ratio levels. It is used together with the mean, not with mode. For the interquartile range, that is just the difference of quartile 1 and quartile 3. So to get the interquartile range of these values, we compute for its quartile 3 first and quartile 1, in which we already computed it a while ago, in which we had quartile 1 as 22 and quartile 3 as 36.5. So to get the interquartile range, simply subtract quartile 3 and quartile 1, which gives us 14.5. To get the lower bound, all we have to do is to apply this formula, which is quartile 1 minus 1.5, this is a constant, times the interquartile range. Since quartile 1 is 22 and interquartile range is 14.5, so we have a lower bound here, which is 0.25. And to get the upper bound, that is quartile 3 plus 1.5, again this is a constant, times interquartile range. We already computed quartile 3 as 36.5 and interquartile range, which is 14.5. So the upper bound is 58.25. Which tells us that if there are values lower than 0.25 or higher than 58.25, those values are classified as outliers. So given this summary in which we have the highest as 41, the lowest is 19 taken from these values, and we already computed the quartile 3, quartile 1, and the median, which is 27, we may construct a graph which is called as the box plot, or also known as the box and whiskers plot, wherein it is composed of a box in which this is quartile 1 and this is quartile 3, and somewhere in between will be the median or the quartile 2, and the whiskers will be the highest and the lowest value. So since we already know that there are no outliers based on the lower and the upper bounds, we may already construct the box plot. And to construct the box plot, all we have to do is to make use of the three quartiles together with the highest and the lowest. And each value here will represent a horizontal line in the graph. So 19 will be somewhere here, just draw a horizontal line. 22 is somewhere here, again draw a horizontal line. 27 will be somewhere here. 36.5 will be somewhere here. So draw a horizontal line. And 41, which is somewhere here, just draw a horizontal line. The three lines in between the highest and the lowest will be representing the box. So again, this is quartile 1, this is quartile 3, and this value is the median or the quartile 2. And we're going to connect the box with the lowest and the highest value using what we call the whiskers. So this is the box plot of this data. Now, given this previous example wherein we added additional observation, which is 222, let's identify whether 222 is an outlier of this data set. And to determine whether it is an outlier, we have to make use of the upper bound and the lower bound. Upper bound will be computed as quartile 3 plus 1.5 times the interquartile range, and lower bound is computed as quartile 1 minus 1.5 the interquartile range. And to compute for the interquartile range, that is quartile 3 minus quartile 1. So we have to compute for the quartile 1 and the quartile 3 first. And computing for quartile 3, which is x sub 3 over 4 of 16 plus 1, that is x sub 12.75. Which again will be computed as x sub 12 plus 0.75 of x sub 13 minus x sub 12. So since this is x sub 12 and this is x sub 13, it is clear that quartile 3 is just 40. And to compute for quartile 1, that is x sub 1 over 4 of 16 plus 1, we have 4.25. Since this is x sub 4 and this is x sub 5, clearly, x sub 4.25 is also 20. Thus, the interquartile range is just 40 minus 20, which is 20. So, quartile 3 is 40, quartile 1 is 20, and the value of interquartile range is also 20. And substituting those values, we have 70 for the upper bound, and we have negative 10 for the lower bound. Thus, a value that's higher than 70 is considered as an outlier. And likewise, a value lower than negative 10 is considered an outlier. And since 222 is above the upper bound, then we can say that 222 is an outlier. Thus, in the construction of the box plot, we're not going to make use of 222. So the highest observation we're going to make use of is 50. The lowest would still be 10. Quartile 1 will be 20. Quartile 3 will be 40. And the median here, which is quartile 2, is 30. So creating a horizontal lines composed of 10, 20, 30, 40, and 50. Again, the three lines in between will be the box. And these are the whiskers. And 222 will just be an asterisk, which is an outlier above the box plot. And that is the one being illustrated in this graph. We may also use the box plot to compare two groups. In this case, we have the box plot of male and female. Similar with the range, interquartile range is presented by reporting quartile 1 and quartile 3. And this is used together with the median, not with the mean and mode. Next is the mean absolute deviation, which is the arithmetic mean of the deviations, which are the distances of the observations from its mean. Now suppose all the 5 students in section A were asked by the teacher to record the number of hours each spent studying for the exam from the time the exam was announced in class, and these values were recorded. Computing for the mean absolute deviation, we have to compute for the mean first. And since these are from all the 5 students in section A, we're going to make use of the population mean, which is 11 hours. Then to compute for the mean absolute deviation, all we have to do is to get the absolute deviation or the absolute difference of each value with respect to the mean. And we know that 9 has a difference of 2 with 11, 15 has a difference of 4 with 11, 8 has a difference of 3 with 11, 9 has a difference of 2 with 11, and 14 has a difference of 3 with 11. Then all we have to do is to get the average of these differences. So 2 is computed as 9 minus 11, 4 is computed as 15 minus 11, 3 is computed as 8 minus 11, 2 is computed as 9 minus 11, and 3 is computed as 14 minus 11. Note that we are getting the absolute difference of each value with respect to the mean. And getting the average of these absolute deviations or absolute differences, we will get 2.8. So the mean absolute deviation is 2.8. Although the mean absolute deviation is rarely used in researches, mean absolute deviation is commonly used in other statistical techniques, like measuring the accuracy of a regression model. So since the mean absolute deviation, which gets the arithmetic mean of those deviations which are always positive, is rarely used in researches, the other way to express the average of those deviations is not by getting its absolute value, but rather by getting its squares. And that's where variance comes in. For the variance, the symbols used are sigma squared for the population variance and s squared for the sample variance. Note that the sample variance uses n-1, not n as the denominator. This n-1 is called as the Bessel's correction. So similarly, we're going to get the difference of these values with 11, but instead of getting the absolute value, this time we're going to get the square. So 9 will be subtracted with 11, so that is 2, or negative 2. When squared, that is 4. 15 when subtracted with 11, we will get 4. When squared, that is 16. 8 when subtracted with 11, that is 3, or negative 3. When squared, that is 9. 9, with respect to 11, the difference is 2, or negative 2, but when squared, that is 4. And 14, when subtracted with 11, we're going to get 3. When squared, that's 9. All we have to do is to get the average of these squares. And that is 8.4 hours. But since these are squared, it is like 9 minus 11, so that's negative 2 hours when squared. That is 4 hours squared. 15 when subtracted with 11, that is 4. When squared, that's 16 hours squared. 8 minus 11, that's negative 3. When squared, that is 9 hours squared. So in other words, all of these are in hours squared. So 8.4 here has a unit which is hours squared. So the variance of these values is 8.4 hours squared. Similarly, if we're going to compute for the variance of these values, we're going to get its mean first, and since these are randomly selected customers, we get the sample mean. And we already computed for the sample mean, which was found to be 28.8 years. Then all we have to do is to get the difference of each value with 28.8, and don't forget to square. So 19 will be subtracted with 28.8, 25 will be subtracted with 28.8, 32 as well, 27, and 41. After getting the square, get the sum, and divide it with n-1 since these are samples. So that is 5 minus 1, and we have 68.2 years squared. By theory, if x sub 1, x sub 2, up to x sub n are random samples from a population with variance sigma squared, then the sample variance s squared, which is computed as the sum of x minus x bar squared over n minus 1, is an unbiased estimate of sigma squared. In which, in simple terms, as long as the samples are selected at random, then the sample variance is neither bigger or smaller than the population variance sigma squared. Now, the reason of using n-1, which is called as the Bessel's correction in the sample variance, it is because theoretically, the sample variance tends to underestimate the population variance. So to increase that estimate of the population variance, we decrease the denominator by 1. The problem with variance is that it uses a unit of measurement that is always square of the original unit of measurement. So it is inconvenient to report that, for example, the mean age of the customers is 28.8 years and variance 68.2 years squared.
Oh no!
So we get the square root of the variance so that the unit of measurement is retained. And that is where standard deviation comes in. Now to compute for the standard deviation of this data, we already computed for its variance, which was 8.4 hours squared. To get the standard deviation, all we have to do is to get the square root of this variance, which happened to be 2.90 hours. And similarly, since we have already computed for the variance of the age of these customers, which is found to be 68.2 years squared, to get the standard deviation, all we have to do is to get the square root of that variance, which happened to be 8.26 years. Note that the standard deviation is used when the mean is reported, not with the median and mode.
Wow!
In the measures of variability, all you have to remember is that the higher its value, the greater the dispersion or the variability of the values from one another. And the lower its value, the more closer the values are with one another. Now suppose you're asked which variable, A or B, has more variation. Consider that the values of A here was just added with 1,000 to get these values. So 5 plus 1,000 is this, 2 plus 1,000 is this, 1 plus 1,000 is this, and so on. That is why the mean just increased by 1,000 as well. But consider that the standard deviation did not change. So to answer which has more variation, it seems like A and B have the same variation since they have equal standard deviation. But what you must consider here is that from 5 to 2, meaning a decrease of 3 in this data set, is a decrease of 60% already. So from 5 to 2, that is a decrease of 60%. As compared to this one, a decrease of 3 from 1,005 is just a decrease of 0.3%. In other words, a change of 1 unit in A has more effect as compared to 1 unit change in B. And similarly, a change of 2 in A has more effect as compared of a change of 2 in B. In other words, A here has more variability as compared with B, but that is not reflected by the standard deviation. So to answer this, we're going to make use of what we call the coefficient of variation, which is the standard deviation divided by its mean times 100%. So whether this is sample or population, all we have to do is to divide standard deviation with respect to its mean times 100%. And we're going to get the coefficient of variations, which is 47.35% in A and 0.16% in B. So this shows that A has more variability as compared with B. In other words, the standard deviation may not be enough to compare the variability of two variables in which the means are very far apart. We use the coefficient of variation not only when the means are different, but we also use the coefficient of variation in comparing the variability of two or more variables with different units of measurement. Like for example, you're comparing the variability of height and weight. Although this ends this part of the descriptive statistics, on the next video, I will teach you how to compute for the descriptive statistics using Microsoft Excel. If you learned in this video, you may click like. You may also subscribe for more updates. See ya!